Today we are going to discuss one of the most confusing concepts of introductory statistics, degrees of freedom of statistical tests. You probably know them from your IntroStats classes where you have to calculate them by hand, or from one of your own works where you need to find them in your favorite statistics program to report them in your thesis or paper. For everyone else with a different background, degrees of freedom are a quantity that have a relation to your sample size and which you use when you are conducting inferential tests, which means when you analyze a sample that stands in for a bigger population, but you don't have any other information about this population, like for instance the mean or the variance. When you do a t-test or a correlation within that sample, you see that the p-value you get depends on this value, the degrees of freedom, in addition to the t or r value that you calculate based on your sample alone. So getting a significant result or not depends on the degrees of freedom. But what is this ominous quantity and why do we even need it? Let's hop into one of the most common explanations. Degrees of freedom are the pieces of information that are free to vary. Often the variance estimation, which I discussed in an earlier video, serves as an example for that. The situation is as follows. You want to estimate the variance of a bigger population, but you only have a sample of that population. You can then calculate the variance of these data points using the mean you also get from these data points. In this case, you need to divide by the degrees of freedom, n-1 in the variance formula, because only n-1 data points are free to vary, or independent. When you know the population mean and do not need to use the sample mean, then you can use n, because in this case all n data points are free to vary. The reasoning goes like this. Suppose you have only one data point, let's say 2. Then someone else tells you they added a second value but don't tell you which number exactly. It might be 5, 7, 138 or any other number. You also do not know the mean of the two data points. The new number is completely free to vary, so the degrees of freedom for those two numbers is 2. The general idea here is that for a vector with two elements and no additional information, these two numbers can be anything given the degrees of freedom of 2. However, when they tell you the mean of both values is 4, then you know the second value needs to be 6. The second value is not free to vary because you can calculate it based on the mean. So the first element of the vector can be anything, but if the mean has to be a certain number, the second is determined as soon as the first one is fixed. So it is only one degree of freedom. When I learned statistics, I found this unsatisfying. First, and this is a question I touched in the other video mentioned earlier, why does it matter statistically when I calculate the mean first, when ultimately the vector itself stays the same? So had the other person not told you the mean, the vector would still be 2, 6, but then with 2 degrees of freedom? But also, what does it mean to say that a value is free to vary? You could argue that after all, no value in real data is really free to vary. Once the data are collected, all points are fixed. So why does it matter at all what I do with them after the fact of collecting them? Mathematicians will probably, and rightfully say, these questions are quite naive, but I think these are reasonable objections from people who are trained in a more applied setting without heavy mathematical background. So to answer this in a way that is more satisfying, at least for me, we can take a look at the geometry of statistics. Basically, we have to take our data and treat them not as data points like it's usually taught, but as vectors, and switch the axes of our coordinate system from variables to subjects. This might seem uncommon, but only because it isn't normally taught that way. When you give it a chance, you will see that many rituals and techniques in statistics become easier to understand. This view and degrees of freedom does not work for all tests you will ever encounter, but for variance estimation, t-tests, ANOVAs, regression, and correlation, it will bring you a long way. In this video, the focus will be on variance estimation and dividing by n-1 instead of n, but the same general idea applies to the other tests as well. Okay, here's an example. Let's use the same list of two data points as before, 2 and 6. In the traditional way, these values are drawn on a number line, like so. Two individual observations of a variable, in this case let's say candy consumption per week. Each variable is a single dimension, so when you have only one variable like we do here, you end up with a line with two observations, 2 and 6. Let's call the individuals eating these candy Anna and Brian. However, why not flip-flop this and picture these two values as a single set of coordinates in a two-dimensional coordinate system? So instead of a one-dimensional line with two individual data points, you get a single point in 2D space. This is a crucial aspect here, so let's repeat that. In the standard visualization, you see each of these numbers on that line as manifestations of a given variable. Here, each individual point reflects how many candies a given person ate in a given week. So you have 2 data points on one dimension, and when you look at your data which has observations in rows and variables within columns, this means the number of rows equals the number of points, and the number of columns, minus the name column, equals the number of dimensions. However, in the other case, it is the other way around. Each row is now a dimension, and each column is a data point, or data vector. In our case here, we only have one. Now each dimension is tied to a given person, and a value on a given dimension reflects the value of that specific person instead of being a common variable candy consumption, where each person has a single entry with a single point. When you add a new observation, like asking a third person about their chocolate bar consumption, you get a new point on the number line in the first notation, and you add a new dimension in the second one. This means the data vector now has 3 entries, but it remains a single vector. But now it is located in 3D space instead of 2D. As a next step, we can partition this vector into 2 parts, which means we split each value of the list into a combination of 2 values. The mean, which is in both cases 4, and the deviations from the mean, the residuals. This is the same you are doing when you are centering a variable, so the residuals here are the same as the original variable, only centered. Our degrees of freedom problem now resides in the second of these vectors. The first is constant, but the residuals vector has the same variance as the original vector, because variance is a measure of spread, and you just shifted all points by the same amount, so the spread remains the same. You can understand the partition as follows. The first mean vector is a simple kind of model with which you explain your data, and the residuals vector describes how well this model explains each data point. A 0 indicates 0 deviation, which implies a good fit for that point. Higher values indicate high deviations, which means the model explains a given point badly. So when there are overall only small values in this vector and many zeros, the model explains the data well. When there are high values, not so well. And of course, all of this translates to more dimension as well, here for our example from earlier with 3 data points. Now let's see how this partition looks from our new geometrical viewpoint. We have 2 vectors now instead of 1, which we are supposed to add together. First, we have the known data vector here in black. It contains the raw numbers of your dataset. We then have calculated the mean of the data points as vector here in blue. We saw earlier that data equal mean plus residuals, so in order to make that equation true, we need to draw the missing residuals vector so that its tail will be at the tip of the mean vector, and its tip will point to the tip of the data vector. This is just how vector addition works. You see that when you follow these instructions, the vector of residuals will always be perpendicular to the mean. This will be super important later. Also note that vectors don't have a real position. They are defined by their length and the direction they point to. So we could also draw the residuals vector so that its tail will be at the origin of the coordinate system like the other 2 vectors. Let's change one more thing. Because the mean vector is just repeating the same number over and over again, we could also rewrite it as being a vector of 1s multiplied by the mean, like so. That does not change anything mathematically, but it makes one important point clear. Every single mean of every n equals 2 sample that you will ever draw will be a multiple of this 1s vector. The mean is just determining how many steps you will need to reach it. The same is true for population means, of course, but more on that later. Okay. Now we are approaching the geometric definition of degrees of freedom, and it is closely related to what degrees of freedom are in a seemingly unrelated field in mechanics. In mechanics, the term degrees of freedom describe, for example, in which dimensions a joint is able to move. The more flexible it is, the more degrees of freedom it has. So your hip has more degrees of freedom than your knees because it can be bent and abducted, while when you try to abduct your knees, it will either not work at all or break and cause serious pain. And now we will see that we can understand statistical degrees of freedom in a related way, as number of dimensions a vector can move in. As discussed before, the mean vector, regardless of the sample, will always be a multiple of a single vector, so it must be positioned on a line in 1 dimension. What about the residual vector? Remember that the residual vector always needs to be perpendicular to the mean vector. Now, because the mean vector is constrained to lie on a single line, and we are in 2D space, the residual vector also needs to lie on a single line, just with a 90-degree angle. So the residual vector can only move in 1 dimension as well, and this equals the degree of freedom it has. We estimated the mean and calculated the residuals based on that estimation, so our degree of freedom is reduced to n-1, which is 1. So we can literally understand degrees of freedom as the number of dimensions the residual vector is able to move in. The next question you might ask is, why do the residuals need to be perpendicular to the means vector? The easiest and also laziest answer is, well, there's just no other way. Remember when we drew the data vector and the mean vector, there was just no other possible vector to make the equation data equals mean plus residuals true other than the one perpendicular to the mean. And it must be true because we calculated the mean based on your data and put everything into the residuals vector what was not already accounted for in the data by the mean. The next explanation is only a little bit less lazy. When you calculate the mean of a list of data points, the mean will be the balance point of this list, regardless of the points. Here we swap the last value in the data, which changes the mean, but in both cases it will be the balance point. This is why the residuals will always add up to 0. Stated differently, for each deviation smaller than the mean, there is another one bigger than the mean to balance. But this has an interesting consequence. When you multiply each element of the mean vector with its corresponding element of the residuals vector, and then add up all the terms, it will equal 0 as well. This must be the case because when the sum of the residuals on their own equals 0, then the sum of these residuals times any other number must also be 0. However, this is just the cross product of the two vectors, and when a cross product of two vectors equals 0, this means the two vectors are perpendicular to each other. My favorite explanation, however, is that your model and the model's errors, the residuals, should be independent from each other because in this case your model will be the best possible one. The idea is that your mean as a model is basically the best single value to represent your data. Any angle between models and residuals vector that is not rectangular would mean that the error vector grows larger and that it also points either a bit along or opposite the means vector, which makes them dependent. This dependency would imply that there is useful information in the residuals which should be in your model, so your model is not as good as it could be. However, independence geometrically means that the vectors need to be orthogonal to each other, and because the mean vector, your model, is fixed to be a multiple of the ones vector, all residual vectors are forced into the line that is orthogonal to that. I will leave it for you to decide which of those explanations you find most helpful, and if you know another one, let me know in the comments below. Now you could say that this is just a happy coincidence for a dataset with two observations on which you should not run statistical tests anyway. So let's quickly sketch the same idea for higher dimensions as well before we show why using the sample size instead of the degrees of freedom would lead to overestimating what we want to estimate, and why this does not apply when we have access to the population mean. Here you see a three-dimensional coordinate system. The blue arrow represents the mean vector. It still has to be a multiple of the ones vector, but this ones vector now has 3 entries instead of 2. But that's basically it for differences. All sample and population means will need to sit on that same line. The black dots are different samples which are connected to this vector by a black line. Each corresponding vector of residuals in orange still has to be perpendicular to that. However, now there is not only a line which would fulfill this constraint, but a whole plane. And planes as two-dimensional objects give the residual vector, you guessed it, 2 degrees of freedom. Now this was all about the sample mean. Remember that you only need to do all that because you don't know the population mean and the population variance. Let's now assume someone had given you the population mean. Remember that so far we only drew samples from a bigger population without knowing this mean value. So our sample happened to be 2 and 6, but there are many more and different samples possible, all with different sample means. The mean of all individuals, or whatever your population is, would then be on average this population mean, in this case say 5, but any individual sample mean can be totally different. This population mean needs to be a multiple of the ones vector as well, so it will be positioned on the same line as your sample mean, but it could be bigger or smaller. Because you have the sample with mean 4, the population mean is obviously bigger in this case. However, the estimation of said mean is unbiased. You are equally likely to draw means that are smaller than the population mean and means that are bigger than the population mean. So when you draw many more samples, you will sometimes overestimate the mean and sometimes underestimate it, but equally likely. We saw earlier that using the sample mean in calculating the residuals will impose a constraint in the residuals vector in the form that it must be perpendicular to the means vector, reducing the degrees of freedom. We see in a moment what that really is about. However, when you do the same with the population mean vector, your result will first be called errors instead of residuals, and second, there is no such constraint. Obviously, the population mean does also not need to be the center of mass of your sample as the sample mean. It can be way bigger or smaller than the biggest or smallest of your individual values. All of this means that the vector of errors doesn't need to be perpendicular to the ones vector, but can move freely in how many dimensions you provide by your data, n instead of n-1. In summary, regardless of your sample, the residuals vector in 2D will be along a specific line. The vector of errors, however, will not. From all that, it follows that the error vector connecting your sample and the population mean can in theory point in any direction. Now, why is that difference important when estimating variance? To explain anything about variance with these vectors, we first have to explain how these vectors are related to variance. So far in this video, we always talked about variation and residuals, but not really about variance. We know variance is the sum of squared distances of data points to the mean, or distances to 0 in case of a centered variable, divided by the number of subjects, in the case of estimation, subjects minus 1. Or stated differently, the average squared distance of data points to the mean. Now remember how we created the vector of residuals. We subtracted the mean from the data points. That is why the elements of the residual vector are the distances to the mean, which get then squared and averaged to get to the variance. And the same is true for the error vectors. So the vectors we calculated so far are part of the variance formula. Here's an example for an intuitive understanding. When our data points are far from their mean, the residuals vector is long because the vector of data points is far away from the ones vector. This also implies high variance. When the data points get closer, the data vector has a smaller distance to the mean vector, so the residual vector shrinks, and so does the variance. We can even go one step further. You can construct a right triangle using the residuals vector and its individual coordinates. The Pythagorean theorem tells us that the length of the vector squared equals the sum of the squared coordinates. But remember that the coordinates are just the data points centered. So this term equals the sum of squares of the variance formula after mean centering. When you have this term, you divide it by the number of subjects to get the average. This is how the residuals vector is connected to variance. Now in our geometrical understanding, a subject is equal to one dimension, because remember that one axis is one dimension. That means we are somehow ignoring one dimension when we divide by degrees of freedom. So why is that? We know that when we just use the sample variance to estimate the population variance, we will underestimate it. This is where all the n-1 correction exists and what I introduced in the other video. But this happens only when we use the sample mean. It is unbiased when we use the population mean. In fact, the bias sits in the sum of squares, which tends to be lower in the left expression. In vector language, this means that the vector containing the residuals is on average shorter than the vector containing the errors. You can also reason backwards here. When you correct for something by dividing by a smaller quantity, that implies the other part you need this correction for must be too small. You might wonder why it then happens to be the case that this average reduction in vector length can be compensated by reducing a seemingly unrelated quantity at a different place in the formula. What happens is that the error vector, which is unknown to us normally, gets projected into a lower dimensional space when we do the estimation using the sample mean. This is a fancy way of saying that what you calculate as residuals is basically a shadow of the original error vector, and you can literally understand it that way. Imagine you are holding a stick in your hand when the sun is directly above you. You can move the stick in all 3 dimensions, but the shadow will always move only in 2, which is the plane under your feet. So when you observe the shadow of the stick, it can never be longer than the actual stick, given the sun's position. It can be the same length, but only if you hold the stick perfectly horizontally. Otherwise, it will be shorter. You can picture this as right triangle with one end of the stick fixed on the ground, in which you will see that the stick will always be the longest side. So when a buddy of yours takes stick measurements using the shadow, while you move the stick around, they will on average make measurements which are too small. The same happens with your vectors. The error vector will always be longer than the residuals vector, except when the sample mean equals the population mean. This is the same case as when you are holding the stick horizontally, in which case the stick and the shadow have the same length. As we saw earlier, like the stick, it can move freely in all dimensions you provide with your data, while the residuals can only be moved in one dimension less than that, like its shadow. You can also see this here. This is the same coordinate system as before, but now I also added the vectors of errors in purple. They are free to move in all dimensions, and when you view them from above, they form the same triangle with the residuals vector as before the stick did with its shadow. So the length of the residuals vector and also its square are too short on average compared to the error vector. Luckily, this is not really of concern to you, only the average deviation for each data point is. So you can correct for the bias in the sum of squares by acknowledging that you lose one dimension when using the sample mean and only measuring the shadow. You see that degrees of freedom in this sense are not directly property of tests like it is often taught, but properties of the data vectors used in these tests. So every time you encounter a test with some degrees of freedom, it is actually a data vector behind this you are doing this test on, which has a certain degree of freedom to grow and shrink, rotate, and so on. I hope this video was helpful to you and that you tune in again into one of my next videos.